30 times faster. That is the staggering statistic we are starting with today.
It's a massive jump.
Right. And I want you to imagine, just for a second, trying to predict today's weather by reading yesterday's newspaper.
Yeah, you definitely get rained on.
Exactly. You're looking at these, old cold front stale precipitation data, and you're trying to decide if you need an umbrella right now.
Which is impossible.
It is.
Yeah.
And that is essentially what artificial intelligence was doing when it was trying to debug embedded hardware.
That latency, it completely breaks the model.
Right.
We have these incredibly sophisticated AI models capable of complex reasoning, but their connection to the physical world, their perception of what's actually happening on a microchip at any given millisecond, it was fundamentally severed by a hardware bottleneck.
They were making brilliant decisions based on information that was, already obsolete.
Totally obsolete, yeah.
So today we are pulling from a really fascinating developer's log, plus a stack of hardware diagnostic notes, to do a deep dive into how swapping a single piece of hardware fundamentally changed how an AI model reasons.
It's a great case study.
It really is. We're looking at this shift from an AI guessing based on stale data to actually, observing a chip in real time.
And moving from a paradigm of delayed reactions to true live observation is a profound shift.
Oh, absolutely.
What's fascinating here is that the culprit was a bottleneck most people wouldn't even think to look for. It was hidden deep in the diagnostic setup.
Okay, let's unpack this. To really visualize what happened here, let's look at the specific environment these developers were working in.
Right, the hardware setup.
Yeah. They were dealing with an STM32 microchip. Now, if you work with embedded systems, you know these chips are ubiquitous. They run everything from, 3D printers to flight controllers.
They're everywhere.
And to see what's happening inside them, developers use a register monitor tool. In this case, a tool called Regmon.
Right. And a register is essentially a tiny ultra-fast memory slot inside the processor.
Like a little sticky note for the CPU.
Kinda, yeah. It holds a specific piece of data or controls a specific function. Think of it as the instrument panel of the chip.
Okay, I like that.
If you want to know what the chip is doing, like its clock speeds, its physical output ports, its timers, you have to read the registers. It's really the only way to know the internal state of the machine.
But the developers hit a massive wall here. The system was reading these registers at a sluggish rate of about 2 per second.
Just 2.
2. You have a processor executing potentially millions of instructions a second, and your window into its brain is updating twice a second.
It's painful to even think about.
Right. That slow drip of data was quietly starving the entire AI debugging process.
Yeah, and the hardware responsible for that starvation was the debug probe they were using, specifically the St-Link version 2.
The probe, okay, explain that for a second.
So a debug probe is the physical bridge. It's the physical device that sits between your powerful desktop computer, where the AI model lives, and the tiny embedded chip you are trying to interrogate.
Ah, okay. And the physical limitations of this older hardware were severe, right?
Hey. The version 2 probe was communicating with the computer over standard USB full speed.
Now, full speed sounds impressive until you actually look at the specifications.
Yeah, the naming convention of early USB generations is definitely generous.
Very generous. In USB terms, full speed means 12 megabits a second.
Right, which is archaic by modern computing standards. But, the USB bandwidth wasn't even the most insidious part of the problem.
Wait, there was something worse.
Yeah. The real issue was that this older probe was silently capping the debug clock, the speed at which it actually talks to the chip, at about 5 megahertz.
That silent throttling is wild to me.
It's so frustrating for a developer.
The diagnostic software would send a command saying, hey, please run this debug interface at 24 megahertz so we can pull this data quickly.
Right, expecting a fast pipe.
And the probe's internal firmware would essentially just nod, ignore the request entirely, and throttle the connection down to 5 megahertz anyway.
Yeah, it just lies to you. And this raises a massive problem for system architecture. When your hardware starts lying to your software, you have engineers and AI models operating on the assumption of a high-speed data pipeline.
When the physical reality is just a trickle.
Exactly. The AI says, read register A. That command travels down the USB cable through the probe, gets translated into serial wire debug signals, enters the chip, grabs the data, and makes the entire journey back.
That's a long trip.
It is. And when you're capped at 12 megabits on the USB and 5 megahertz on the chip interface, that round trip takes an eternity in CPU time.
So the AI spends almost all of its time just waiting.
Pretty much,
It's
yeah.
like replacing a multi-lane highway with a single-lane toll booth where every single car has to stop, roll down the window, and pay an exact change.
That's a great way to put it.
The cars, or the data packets, don't just have less room, they're fundamentally forced to stop moving. I can see how that completely strangles an AI's ability to analyze a chip.
It totally does.
It's trying to find a flow state, but it's constantly hitting a red light.
And because of that, the AI is starved of context. If an AI is going to interact with the physical world, its sensory inputs have to operate at a speed that matches its cognitive processing.
Otherwise, it is effectively blind.
Right.
So the obvious solution when your hardware is lying to you and choking your data is to just replace the hardware entirely.
Throw it out.
Exactly. They swapped out the version 2 probe for the ST-Link version 3.
And the architectural leap between those two versions is dramatic. The version 3 probe utilizes USB high-speed, which jumps the data rate from 12 megabits to 480 megabits a second.
Wow, that is 40 times the data rate of the old probe.
Yeah, and crucially, it respects the software.
It actually listens.
Finally, when the diagnostic tools ask for a higher clock speed to talk to the chip, the version 3 probe actually delivers it.
So we swapped the exact change toll booth for an open road electronic transponder system.
Data just flows.
Right, the data doesn't stop. They realize the version 2 is the bottleneck. They get the shiny new version 3 probe with its massive speed upgrade. They plug it in, and, well, the whole system immediately fails.
Because the transition from theory to practice is rarely elegant.
It really isn't. And this brings us to what the developer's log described as a Sunday afternoon troubleshooting reality check.
Oh, we've all been there.
The sequence of failures they went through before the breakthrough is just a perfect look into the messy human reality of hardware engineering.
It highlights the frustration of chasing down diagnostic challenges. I mean, you have this incredibly advanced setup, cutting-edge AI models, complex microcontrollers, and the very first point of failure is the most basic physical connection imaginable.
Right. The new version 3 probe wouldn't even show up on the computer.
Nothing.
The power light is shining brightly, just mocking them, but the machine is completely blind to the USB device. And I love this detail from the notes.
Oh, the log.
Yeah. They checked the kernel log, the operating system's lowest level internal diary, and the computer literally printed out the message, maybe the USB cable is bad.
That's amazing. The operating system throwing its hands up in defeat is always a funny moment.
It really is.
Usually kernel logs give you cryptic hex codes or dense driver errors. When it just resorts to check the cable, you know the failure is entirely at the physical layer.
It's the absolute oldest trick in the book. All this high-level AI reasoning foiled by a faulty wire.
Always check the cable first.
Right. So they swapped the USB cable, and suddenly the computer could communicate with the probe, but they hit another wall immediately.
Of course they did.
The computer could see the probe, but the probe couldn't see the chip.
Right, so they moved one layer deeper into the onion. The system started throwing a failed to enter SWD mode error.
Okay, for people who don't know, what is SWD?
SWD stands for serial wire debug. It's the standard protocol used to program and inspect these ARM-based chips. It's essentially the raw nervous system tap into the microcontroller. And it only uses two pins, one for a clock signal to keep time and one to pass the actual data back and forth.
Got it. And to make matters worse, the diagnostic tool was returning a chip ID of 0.
Which is never good.
Now, my understanding is that a chip ID is essentially the silicon's official signature. It tells the probe, I am this specific model of chip.
Exactly.
So a chip ID of 0 basically means the data line is just dead silent, nobody is home.
Right. A 0 means the data line is pulled low and nothing on the other end is driving it high. It's absolute silence.
So what was causing that?
Well, the developers chased this dead silence through 3 different circuit boards before they realized what was actually happening.
3 boards?
Yeah. It all came down to the physical topology of the test board they were using and a completely logical but completely false assumption.
Okay, let's dig into that topology. Why did the machine start lying to them about where the signals actually go?
So they were using a specific type of evaluation hardware called a discovery board. These boards are designed primarily as cheap, all-in-one educational tools for students and hobbyists. Because they're meant to be an all-in-one package, the manufacturer actually builds an ST-Link debugger directly onto the board itself.
Ah, That way, a student doesn't have to go out and buy a separate $100 probe just to learn how to program the chip.
Exactly. It's a great design for a student.
But these developers were trying to use their own professional-grade version 3 probe.
Right. And they saw a debug connector on the board and just naturally assumed that was where they were supposed to plug in.
Makes sense.
Yeah, the developers assumed that the debug connector on the board was the input, the place where the SWD signals were supposed to go into the chip they were testing.
Yeah.
But because of how these educational boards are designed, that connector wasn't an input at all. It was an output.
Wait, it was an output?
Yeah. The physical connector they were plugging into was the output for the board's built-in debugger.
Oh, no.
It's designed that way so you can use the cheap development board to program an entirely different external chip on a custom circuit board.
So they took their brand new lightning-fast version 3 debugger and plugged it directly into the output of the built-in version 2 debugger.
Exactly.
They literally had two debuggers facing each other, screaming into the void, while the chip they actually wanted to talk to was sitting completely isolated.
That is exactly what happened. What's fascinating here is how easily smart developers can make false assumptions about hardware routing when they apply professional expectations to educational hardware.
Right, because the board wasn't broken.
The board wasn't broken, the probe wasn't broken, the software was fine. They just fundamentally misunderstood the physical topology of the hardware in front of them.
It's a great reminder that before we even get to AI reasoning, human reasoning has to get the physical layer right.
Always.
So how did they bypass this confusing topology?
Well, they had to ignore the board's built-in routing entirely. The real SWD pins for the chip, specifically pins PA13 and PA14, which are the literal physical metal legs on the microcontroller package dedicated to debugging.
Right.
Those were broken out on the standard header rows of the board.
Okay, so they could get to them directly.
Yeah. They took raw jumper wires and wired the version 3 probe straight onto those specific pins, creating a direct pipeline to the chip's nervous system.
Direct access. And according to the notes, that is when the magic finally happened.
It instantly works.
The probe instantly saw everything. It read the correct chip ID, which was 0x440, and that just tells the software exactly which family of STM32 chip it's talking to.
Right.
And it saw the 64 kilobytes of flash memory. The physical connections were fixed, the dead silence was broken, and the data could flow.
And this is where the performance metrics become incredibly revealing because the bottleneck in the system shifts entirely.
Okay, let's talk about those metrics. The register reads absolutely skyrocketed.
Oh, big time.
They went from that agonizing 2 reads a second all the way up to 59 reads a second. Every single read pulling live, actionable data.
It's a huge improvement.
It is. But I want to push back on the math here for a second because something doesn't quite add up to me.
Okay, let's hear it.
The new probe is communicating over USB at 480 megabits a second.
Right.
That is 40 times faster than the old 12 megabit probe.
Correct.
But the read speed only went up from 2 reads a second to 59. That's about 30 times faster.
Ah, I see where you're going.
If the USB pipe is 40 times wider, why isn't the data moving 40 times faster? Does the silicon itself have a speed limit?
That is the crucial question, and it's what the developers investigated next. Because yes, the silicon absolutely has a speed limit.
Okay, explain that.
You have to remember that the microchip is a physical piece of hardware running on its own internal clock. When the probe sends an SWD command to read a register, the chip's internal hardware peripheral has to physically fetch that data from its memory banks and push it out through the pins.
So the speed limit isn't just about how fast the USB cable can carry the request.
No, not at all.
It's about how fast the chip can physically answer it.
Exactly. To test this, the developers dynamically changed the chip's own internal clock speed.
Oh, that's smart.
Yeah. So when they ran the microcontroller at a relatively slow heartbeat of 8 megahertz, the register reads topped out at about 49 per second.
Interesting.
The SWD peripheral inside the chip is synchronized to that core clock. It simply couldn't fetch and spit out the data any faster than 49 times a second at that speed.
But when they cranked the chip's internal clock up to 48 megahertz.
Then the read speed jumped up to that maximum of 59 per second.
Okay, wow.
The key insight here is a profound shift in the system architecture. The version 3 probe is so fast that it has entirely removed itself from the equation.
Right. The probe is no longer the bottleneck.
Nope. The limiting factor is now the physical silicon of the chip itself processing the requests. They maximize the observational capacity of the hardware.
Okay. If the chip is running at 48 megahertz and we are only reading it twice a second with the old setup,
Yeah.
that means the chip has lived entire lifetimes, executed tens of millions of instructions between our snapshots.
It's bonkers when you think about it.
And that brings us to the core of this deep dive. We've established the hardware fix, we've bypassed the bad cables and backward connectors, and we've hit the physical limits of the silicon.
We're finally at the software side.
Right? How does reading a register 59 times a second instead of 2 times a second fundamentally transform artificial intelligence?
So to understand that, we have to look at how a neural network approaches troubleshooting a live system. It relies on a procedural loop. The AI reads a register to understand the current state of the chip. Then it uses its model to reason about what that state means in the context of the bug.
Makes sense.
Next, it writes a new value to a register to try and fix the problem. And finally, it reads the register back again to verify if the fix actually worked. Read, reason, write, read back.
Okay, so if an AI is reading and writing to fix a problem, but its read is half a second old,
Yeah.
it's basically trying to catch a baseball while wearing a blindfold. It knows a ball was thrown, but has no idea where it is right now.
That's a perfect analogy, because in embedded systems, a microchip can change its internal state millions of times in that half-second window.
Wow.
If the AI is acting on a half-second-old snapshot, it is reasoning about a chip that technically no longer exists.
It is a historical artifact.
Exactly. The AI might deduce a brilliant solution, but it applies that solution to a state space the chip has already moved past. It's like playing a competitive online video game with a 500 millisecond ping.
Oh man, the worst.
Right. You shoot it where the target was, not where they are.
So what happens to the AI's logic when you finally take that blindfold off? When you collapse that feedback loop from an agonizing delay to a fluid, real-time conversation at 59 reads a second?
It changes the entire nature of the interaction. The neural network's context window expects a continuous state space, not discrete, disconnected snapshots.
Right.
At 59 reads a second, the AI reads a register and acts on it in the same computational breath. The latency between perception and action essentially disappears.
So the AI's internal model is finally in sync with the physical reality of the hardware.
Completely in sync. Faster register feedback cycles don't just shave off milliseconds of boredom for a human operator watching a progress bar on a screen.
Right. It's not just a quality of life thing.
No, it fundamentally changes the validity of the AI's reasoning. This is the literal difference between an AI guessing what to do based on a stale memory of the chip and an AI truly observing the live dynamic state of the hardware.
Here's where it gets really interesting. If you want an AI to debug physical hardware, high-speed monitoring isn't just a nice-to-have upgrade.
It's an absolute observational necessity.
Exactly. When the register data becomes truly live, the AI can probe a timer, adjust a GPIO pin, and probe again seamlessly. Its reasoning is grounded in the absolute present.
Yes.
Just by upgrading the physical pipe, by ditching an artificially throttled 12 megabit connection for a 480 megabit live feed, you completely unlock an AI's ability to reason about the physical world.
You allow the AI to be as smart as it was designed to be. The software can finally trust the hardware.
We have covered incredible ground today. We started with a staggering 30 times speed increase for AI debugging.
It's been a journey.
We navigated the sheer relatable frustration of bad USB cables and backward upside-down debug connectors on educational boards.
The Sunday afternoon special.
Yes. We explored how the physical clock speed of a silicon chip dictates how fast it can share its secrets. And ultimately, we saw how collapsing the latency in a feedback loop transforms an AI from a historical guesser into a real-time observer.
And it's really worth reminding ourselves of the human element in all of this.
Definitely.
This wasn't just a sterile, theoretical hardware upgrade. This was a messy Sunday afternoon of chasing unexpected faults. For anyone in engineering, that hands-on diagnostic challenge is often where true understanding comes from.
Right. The struggle is the point.
Exactly. Finding that bad cable, realizing you misunderstood the board's physical routing, testing the clock limits against the silicon. The speed increase was the prize, but the fault finding was the journey.
The machine pushes back, and you have to figure out why. Which leaves me with one final thought for you to mull over.
Let's hear it.
We spend so much time obsessing over making our AI models smarter. We pour billions into making their algorithms more complex, their neural networks deeper, their training data vastly larger.
Sure, constantly pushing the software limits.
But if an AI is truly only as smart as its observation window, What other cutting-edge software in your life is secretly being held back by a physical bottleneck, patiently waiting for someone to upgrade its eyes?
It's a great question.
Until next time, keep diving deep.